that, thank you. Thanks for the kind introduction. So it's my real pleasure being here. Not only do I like traveling to Brazil a lot, I think it's a great country, but I think Brazil has also come a long way from a technology perspective. I just looked into some numbers yesterday on where Brazil stands, and I found that there are about 300,000 startups that are being created every year in Brazil now. And from an internet perspective, 64% of all internet users connect from mobile. And from those 64, 86% actually have access to 3G networks, 2G and 3G networks. So I think this is a really great time to get started with real-time communication and thinking about how to enable those users on a real-time basis with WebRTC. And that's why I'm here, to talk with you and to you about WebRTC and give you a status update where we are and how we got there. So I'm starting off with a status update, just giving you some numbers, what we see of WebRTC usage in Chrome from those users who opt into providing this data to us in Chrome, but also how the ecosystem has developed. I'm going to do a quick 101 on the WebRTC overall pictures, and I think we've seen already and heard really great presentations today. I also learned quite a bit about WebRTC actually, and I will look into, give you an overview of features that we have developed and launched this year, and what's our roadmap basically towards end of the year and beginning of Q1. So about 5 years ago, on June 1st, 2011, my colleague Harald, who works with Varun on the GetStats specification, posted to a W3C mailing list that we are open sourcing WebRTC and working on standardizing web APIs for real-time communication platform. So 5 years fast forward. On June 1st, 2016, we celebrated the 5th year's anniversary by updating the logo until end of this year. And what did this 5 year basically bring into launching a toolkit basically for real-time communication and enabling users to make use of RTC in the browser. So just 2 weeks ago on the Chrome Dev Summit, it was published that there are 2 billion Chrome browsers across the desktop platform and also mobile, which are active every month. These are monthly active users, and all those are WebRTC enabled. All those are WebRTC built in, and you can basically directly enable all Chrome users by making use of the web APIs that we have. But it's not only Chrome, right? Since we launched WebRTC, WebRTC has been adopted across various browsers. So this is an overview, basically, of which APIs are enabled by which browsers. And you see there are quite a few now, and not every user, obviously, is a Chrome user. People make use of different browsers, but many of them are WebRTC enabled. Microsoft on the Edge Web Summit provided this update on WebRTC development status, and I'm super happy basically to see really Microsoft joining basically the bandwagon of WebRTC, and I think there's actually one update to this slide that VP8 for real-time communication is now also in development in Edge. So you will have basically various options from a codec perspective to connect users across different platforms. There was a question about WebKit earlier ago, so there are some folks who have brought Open WebRTC, an alternative implementation of WebRTC, into WebKit just some weeks ago. And here you see a AppRTC video call between a WebKit-enabled WebKit GTK Plus browser and Chrome. So WebRTC is actually already somehow there in WebKit, but if you look on the WebKit side, you see also the official status of under development. So eventually also WebKit and other browsers that build on top of WebKit, hopefully, will also be WebRTC enabled. And these WebRTC browsers are being used. It's not only they're all enabled, you know, and sitting there around on some desktops and mobiles. So what we see in Chrome, that we have an aggregated usage of audio and video minutes per month of 1 billion. Well, that is 2,000 years of audio and video communication per week. What is being used only in Chrome by various service providers. But it's not only audio and video communication that we think of WebRTC, right? It's also the data channel that has been mentioned today. And what we see on in Chrome, again, for the data channel is per week is 1 petabyte of data transferred over the data channel. And that is for various use cases, right? There are services that provide content delivery networks, CDNs in WebRTC, but this is also any kind of content sharing basically for peer-to-peer. So this is massive. In the end, it's only 0.1% of all Chrome traffic, but this number has been rapidly growing. So just beginning of this year, this was at 0.05%, and now basically we doubled this, or users, you all and all WebRTC users have doubled this with the services provided over the data channel. And it's spread across different projects and companies that make use of WebRTC. So by launching this toolkit as open source and providing the codecs, which we have talked about already today and which I will dig into a little bit later on, we've really unlocked basically the previously closed ecosystem of real-time communications. So 1,200 WebRTC-based companies and projects that are tracked by Sahib on his blog. And this is great because it's not just a few players that basically own all the services on users. It's tons of projects and services that make use of it now. It's not only a phenomenon of the web, so some estimations that we have done just by knowing what kind of services built of WebRTC shows us that there are probably around more than 5 billion apps that have been downloaded which include WebRTC on iOS and Android. So what are those services on mobile? We have just launched our own reference service or communication service on top of WebRTC, which is Duo. This August. It's been used a lot actually here in Brazil, but there are quite a lot of other mobile apps that make use of WebRTC. It's Viber, for example, that makes use of part of it. Hangouts obviously builds on top of the WebRTC stack. Facebook Messenger builds on top of WebRTC, so if you want to make a voice call or video call inside of Messenger, it's WebRTC that is being shipped with it. Snapchat, as being mentioned by Sahi earlier today, the video calling service in Snapchat is based on WebRTC, and Slack has just some month ago launched basically audio calling in Slack, and this is also based on WebRTC. These are numbers that we don't see, but if you think about the 1 billion minutes per week, only in Chrome, and now you basically multiply this across all those apps, it's probably much, much more usage that is being made on top of WebRTC. And the phenomenon is global. So Brazil makes it under the top 20, but these are the Google trends for WebRTC search queries in Google. And you see this has been growing continuously over the last 5 years. And it's being spread around the world. So it's China who's making basically most of the queries, which is very interesting, but then also South Korea and Taiwan. So this is, first of all, like an Asian phenomenon, but it's also Sweden, India, and US, I think, doesn't even make it under the top 7. So it's nice to see that it's not really like the Western tech countries who adopt this, but you can see it all over the world, that users and servers are investigating how to bring real-time communications to all internet users. So let's dig a little bit into WebRTC for those of you who might be newer to it. So this is the overall architecture picture that we are living with in a couple of years in WebRTC, and I just want to quickly walk you through basically top to bottom. So we have seen the web APIs already, and those were covered extensively basically today already. But there are also mobile APIs which are provided by the mobile native libraries for iOS and Android that we are providing. These are either an Objective-C or Java bindings that you have there. And below those application level APIs, you have the C++ peer connection, which is like the main interface basically to the WebRTC library. And below those you have 3 big components. One is the voice engine, as we call it, which includes all the audio codecs. This is Opus, Isaac, and G711 that is enabled in WebRTC. And which has a jitter buffer, which we call NetEQ, the net equalizer. So this jitter buffer basically takes care of all the incoming packets and trying to do packet concealment if there are packets lost, or trying to manage basically the variability that we see in delivery of the packets. And then we try to address certain very hard to solve signal processing problems in software. So this is echo cancellation, noise suppression, and gain control. And this in the end basically what helps to make audio great and tries to fix many problems with different hardware that we see. There's a video engine basically which enables WebRTC with video communication. So the codecs that are being provided are VP8, VP9, and H.264. And similar to NetEQ on the voice side, there's basically a video jitter buffer that manages the incoming packets and the incoming packets for video communication. And the underlying algorithms that enable a best quality video communications in WebRTC is bandwidth estimation. So WebRTC is mainly used in the internet, right? It's not usually, or the telcos, I would say, are not the usual users of WebRTC. So we are not operating on a medium with a dedicated quality of service. We don't actually know what kind of bitrate and quality we have for each individual sessions. You can do tests in advance, but actually the next time your network quality might be completely different because the internet, and especially Wi-Fi, is a shared medium. So bandwidth estimation is a key component to understand and to deliver video. And then obviously it's like error correction. If you lose packets, how do you deal with those? Can you apply even forward error correction in providing more bits and fixing those errors that might occur? And then there's a transport component. So each communication in WebRTC is always encrypted. There's never unencrypted communication. So SRTP, and I think stun, turn, and ice has been extensively covered already today here, but this is basically the mechanism that we have built into WebRTC that helps you to cross the network translation. That is applied in many IP version 4 networks nowadays. And then we have those platform-specific connectors. So every operating system, every hardware is having its own audio capturing and rendering, video capturing and rendering, and network I/O system basically to which we need to adopt or connect to from a WebRTC software perspective. So bandwidth estimation, beginning of this year, we had about 2 seconds medium ramp up time to 1 megabit video. That means bandwidth estimation, the algorithm used 2 seconds to understand what is the capacity of the network and to be able to ramp up to 1 megabit, which provides an almost HD stream. Since then, we have made great changes to bandwidth estimation. We switched the algorithm from a send-receive side split algorithm, moved all the logic of bandwidth estimation into the send side, and worked on a feedback format which is provided from the receiver side back to the send side. And this allows us to basically decrease the time of that we need for ramping up to 1 megabits to 650 milliseconds. So this is below 1 second. And this is, for example, why Duo works so great and why we can do something like knock-knock with a good video quality from the very beginning, because we get instantly very good video quality. The codecs, as I mentioned, in WebRTC are our own codecs from the WebM project, VP8 and VP9. They're both provided with libVPX inside of Chrome. They're open source and royalty-free, so everybody can use them. And the work that has been started there is now being continued in the Alliance for Open Media, which not only all big internet players more or less have joined, but also, and this is very important, the chipset manufacturers have joined, or many chipset manufacturers have joined the Alliance for Open Media, and this really provides basically assurance that the next generation codec will also be hardware enabled. The other codec that we committed to support is H.264, the legacy video codec basically. So we make use of Open H.264 here for encoding video in WebRTC, and Chrome always had libffmpeg for decoding H.264, which is also used for WebRTC. But we went basically beyond this and thought, okay, if you want to make it efficient, if you want to address the capabilities of the devices, we also implemented the hardware encoders on desktop where it is available. So that is on Mac OS, Chrome OS, and on Windows selected machines. And if you have basically H.264 hardware encoding in there, Chrome automatically makes use of it. And this saves you battery. This reduces the heat of the machine and the time basically until the fan turns on. So I want to give you here an idea what is the advantage actually of VP8 versus VP9 and why we call VP9 the successor of VP8. The great thing is that it requires 30% less bits. So I will jump out of this presentation, go in here, and this is an example video that I'm starting now. And the left side shows VP8 at 800 kilobits per second, whereas the right side of this red line makes use of VP9 at 650 kilobits per second. And both are on HD resolution. So usually, if you see here, I'm sliding on the white background, there's like hardly any difference. Looks boring, is actually exciting, because these white backgrounds is usually where you can very see when there's a lot of compression happening in the codecs, and then those look very different. But also, if you look basically on Marco's shirt, like hardly any difference, or also the skin color. So I show you here basically two sides of this video, and there's no difference. And this is actually the great thing that I want to outline here. Going back into some numbers that we have from YouTube, which has enabled VP9 already in large scale. So in 2015, there were 25 billion hours of YouTube video shown making use of VP9. So think about 30% less bits on such a scale. That is huge for network providers on traffic that needs to be delivered. That is huge for YouTube on capacity for play out, but this is also huge for content creators and connecting their users with them. Excuse me. Oh, this is another graph provided by YouTube. And you see here, Brazil is here on number 4, basically. And this is the amount of users that VP9 enabled to upgrade to an SD resolution. And SD is actually something on mobile where we say, like this, an acceptable video quality. So over 10% of users in Brazil were, due to VP9, upgraded to an SD resolution where they had before very low resolution. So now think about the potential of real-time communication, right? You provide better video quality to your video communication service, even if the network capacity is not that great. That might be on your 3G network, for example, or on your bad Wi-Fi. So VP9 is a more complex codec than VP8. Some of you may say it's difficult to run this basically in software on the devices, but our tests have shown that at these rather small resolutions, it's feasible. So you can actually make use of VP9 also on mobile if you run at those small resolutions. The audio codec, as been mentioned before, is Opus, which is our codec of choice. It's also an open source project. We continue to invest into Opus massively, mainly for reasons of improving quality at the ultra low bitrate range, so somewhere between 12 kilobits and below. This is if you have a rather good edge connections or a pretty bad 3G connection. You should still be able to have, if you don't have huge packet loss or delay spikes, you should still be able to run a voice call at those bit rates. But we also try to increase the complexity. So increasing in complexity provides in general higher quality of the Opus encoding. And for being able to doing this, we basically work a lot on performance. So let's look into some of those features that we have launched this year and I'll continue to launch towards end of this year. So one of the most start features in WebRTC this year was Media Recorder. There were actually over 2,500 stars. It was the highest start bug in the Chromium bug tracker. And what it does, it supports the recording of local and remote media streams. So this is not necessarily an API that you want to make use of enable real-time communications, but you can basically capture your screen or capture any incoming stream with this API. You can capture it in VP9, VP8 or H.264, and the default codec is set to Opus audio. So we see that this API is being picked up. We don't really know what's happening and why people are using it. And we would really love to hear basically back, what are your use cases? What are the kind of services that you, from a developer's perspective, are working on to record media on a host? We worked a lot on bringing more performance to iOS. So mobile is a focus for us, obviously. And performance on mobile is always critical. So on iOS, we worked a lot on with the texture pipeline, and that helped us to decrease the power consumption by 18% by being able to capture directly to textures by reducing or removing copies of frames that we have done before. And especially if you think of the iPhone 4, 4S or 5S devices, this is where it becomes critical that that these performance improvements really make your service smooth. But Android obviously has been also in the focus. So WebRTC Mobile, WebRTC has been mentioned before. It's a free service that we offer just for trying out WebRTC. There's also a mobile app which is called WebRTC Mobile. And by making use of capture texture, for example, and reducing removing frame copies in the capture process, we reduce the power consumption. So don't be fooled by these graphs; they look kind of equal. But if you look on the y-axis here, you see that the scale is different. So this is just the battery power that has been removed. This is basically CPU improvements that we have done. And we have also enabled offloading to the GPU. And this is how the GPU load looks after all these improvements. So these are massive improvements that we have done in the stack inside of WebRTC to help you from a developer's perspective to create better services on mobile. From an enterprise perspective, or not only that, but mainly from an enterprise perspective, screen sharing is an important topic. So what we have done is to enable screen sharing on Android. So it captures everything that is on the mainstream screen. It's just being launched now in M55, which is coming out soon, but it's already used. It's used in the Pixel phone that we have launched. If you have issues with your Pixel phone and don't know how to use it, you can call a help hotline. And the help hotline asks you if you want to share the screen with the backend or with the hotline agent. And the hotline agent is then able to annotate the screen and provide drawings to the user on what buttons to touch, on where to go on the screen for doing things. And this is WebRTC enabled inside of every Pixel phone. We've also enhanced and improved screen sharing on the browser. So in Chrome 54, we enabled tab sharing. Before that, it was always share your entire screen or share an application window. So now in Chrome, you can also just share a specific tab with other users being connected in a call. And you can see that we have organized the screen picker UI differently. It makes use of material design now as a UX. And we have organized it differently and hopefully more intuitive. So you can share your entire screen, the application window, or the Chrome tab. And additionally, you can share your system audio. So we received many requests, actually, that users want to share also audio in screen sharing sessions. And for tab sharing, this can be done across all different platforms. This can be done on Mac OS, Windows, and Linux. Whereas the system audio sharing is not always available. So we will share the slides later on with you, but there's also a URL on here where you can try this out by also installing an extension for this. WebRTC is also used a lot in corporate networks, in enterprise scenarios. And often these corporate networks are managed and blocked or protected by firewalls. And that means that UDP is limited to often to a specific port range and not across all the range above 1024 usually, port 1024. So what we have done, we have enabled a Chrome user policy that the administrators can specify the port range for which it allows WebRTC traffic. And then WebRTC is forced, so all UDP traffic in WebRTC is forced to go through this specific port range. This has been a much wanted feature from all big service providers that make use of WebRTC. So what's the upcoming work that we are focusing on end of this year and beginning of next year? It's making WebRTC better, even when there are proxies that require authentication. There are still a few bigger bugs, I would say, that prevent WebRTC from being like having really the 5 nines of reliability. High FPS, frame per second screen sharing, and what we call slim WebRTC. So I want to briefly walk you through these features. So, yeah, WebRTC works best with direct UDP. It can fall back to TCP, but in many corporate networks, there's a proxy which requires all traffic that goes in and out to be authenticated. So there are 2 different stacks basically in Chrome. One for the HTTP signaling side, and then one for the media side from a network perspective. And whereas proxy authentication works well since a long time for the HTTP signaling, it does not yet for any media traffic. So what we will be working on until the end of this year together with the Chrome team is to enable basically the media side also with proxy authentication. And that will enable the media traffic to pass through these proxies in such a managed environment. And you see that this feature request is having over 100 stars. So in general, if you want basically features to be prioritized in our work, starring a bug is always a good idea, because then this is a feedback mechanism to us where we understand what is really wanted by the community. Improving media reliability. So there are still 3 main issues that we see where Chrome and WebRTC fails from time to time. One feature is there's no audio from microphone coming in. We actually see the microphone, but we all get zeros all the time. So, and you need to restart Chrome to make this happen or to fix this. A similar issue is there's no webcam detected, and you need to restart Chrome to get the webcam back enabled. And then there are from time to time glitches on the audio and video render and capture side. So these are fundamental problems that we have with WebRTC inside of the Chrome architecture. It's due to how processes are being managed inside of Chrome and how different processes are competing on threads. And what this means to us is we need to switch basically the process handling for media in WebRTC. And there's a new process framework in Chrome which is called Mojo. It's a simplified process model, and it addresses basically data ownership and process sharing. So we will adopt Mojo for audio and video capture. They will get their own processes. They will not compete against other processes anymore inside of Chrome. So if you have very heavy and expensive JavaScript in your application, this will not block the audio or video capturing or rendering anymore. And video will come first until end of this year, and audio is a little bit of a bigger project. And this will land basically next year then. And this will be a big milestone for us, because then we believe that really WebRTC will become very stable inside of Chrome. Another feature that we are working on is high frame per second screen sharing in Chrome. So the idea is to enable users with sharing video or multimedia content, sharing gaming via Chrome. This is the feedback that we have received. So we are adopting a new DirectX feature for desktop capture. It allows us to go up to 30 frames per second, depending on the power of the desktop hardware. And this will bring almost real-time screen sharing into Chrome. Last but not least, Slim WebRTC is a project with which we address the requests from many users who want to customize WebRTC. Not always do you want to ship all codecs with WebRTC, or you want to deploy WebRTC to constrained devices because you are building a camera or a speaker or a microphone which is all network connected from an Internet of Things perspective. Though WebRTC might be too big, basically the footprint might be too large of the binaries. So we are coming up with a way of allowing you to configure the WebRTC libraries on a modular basis, removing specific features and customizing it to your needs. So to sum up what we are doing with WebRTC, the WebRTC platform on the web is moving towards a very stable state. We see tons of services being built on top of it. There's a lot of usage, it's massive usage. We ourselves have at the moment an increased focus on mobile to bring up the mobile platform on an equal state from a performance perspective. And we invest tons of time and efforts to make WebRTC better when the networks are not so good. And I think this is especially something in markets like Brazil, on mobile networks where we hope to make WebRTC to work much better. So I thank you for your time and being here, for listening to me, and yeah, are there any questions that you would like to ask me?